Okay, so today we're starting on the first part of this next semester is built primarily on this thing called inference. So inference is, of course, when you probably hear it mostly in English. What are you trying to do in English whenever you hear about inference? You're trying to infer about what? Maybe what the author means or the meaning of whatever that symbol is, that kind of stuff. Okay, well, in statistics, this inference that we're going to be doing, we're going to attempt to infer something about the entire population just based on one little itty-bitty sample. So that's a big deal to think that you want to infer about an entire population based on a little itty-bitty sample. And so there are two different kinds of inference that we're going to learn about this semester. And the first one is a confidence interval. So here's what a confidence interval is going to do for us. A confidence interval is what you would make when you want to know what a particular parameter is. And so I want to define that word parameter because I'm going to use that a lot this semester. And so parameter is a population's value. Okay, so if I was going to want to estimate the average length of rattlesnakes in Texas, if I want to estimate the average length of all rattlesnakes in Texas, then of course I cannot measure them all. So I would take a sample, and then from that sample, I would then estimate the average length of all rattlesnakes. So, and then hypothesis testing we'll do later after that. Now, we're first going to deal with confidence intervals, and we're going to attempt to predict or estimate the proportion of water on these little toy globes that I have, like little beach balls. It's a beach ball that I blew up of the world. And so we're going to estimate the proportion of water on the globe. So let's actually define that parameter. So P equals the proportion of water on our toy globe that we're going to be dealing with. Okay? So I would imagine if you're going to make an estimation, if you're going to make a claim about an entire population from one little itty-bitty sample, then you probably want to make sure that the conditions have been met for inference and that we have the right to do this and you feel like it's a representative sample. So conditions are our typical get real. So our first one's going to be random. And so let's do that with our globe tosses. So we're going to toss the globes in the air and we're going to see how frequently a little pinpoint on our finger lands on water versus land, the proportion of times that it's landing on that. So we're going to assume that the 50 globe tosses are randomized. We will be doing a sample size of 50. And so when you toss these globes from person to person, you'll want to make sure they spin nice and get randomized. Okay, independent. So for independent, we want to say N, which is 50, is less than our 10% of all globe tosses. Okay. And then we have large enough. So, what type of large enough will this particular problem have? Since we're going to be talking about the proportion of all water on that toy globe, what do we have to have? N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10. So, the thing I want to ask you about, though, is, I know N is 50, but what is P? What is the true P for this? Do we know the true proportion of water on the globe? I mean, now we could use the real globe, but that's not what's on our toy globe necessarily. So you know what? We do not have true P. That's an issue. If you do not have true P, of course, if you have true P, that's the best it can be, and you want to use that. But if you don't, then you will use the next best thing you have, which is P hat. So the best it can be is if you use true P. But if you don't have that, you can just use P hat. Okay? So we have some, issues with how confident we are in our data because we're using a sample instead of the true population. So we're going to have to come to this after we collect our data and you all get your own P hats. So here in a minute, you guys are going to collect your own P hats and see if you have at least 10 successes and at least 10 failures. All right. So if you would, scoot on over a couple of pages to page 3 where we talk about let's collect some data. So here is how we are going to do this. We are going to put a pinpoint on your finger because you're going to be catching this globe and your finger is quite large. And so when you toss this beach ball in the air, this globe beach ball, and Carly, will you throw me one of those beach balls back there? Perfect.
Oh, that's so embarrassing.
There you
Sorry.
go.
That's harder
That's
than
okay.
you think.
There you go. It is. Okay. Can I use your pen?
Yes.
Okay, so see, here is our beach ball globe. And so if I just toss it and I have my finger on here, my finger's so huge, it's half on land and half on water. So you're going to take your pen and put a little point on your finger so that then whenever you toss it, you can see if that point is on water or land. And FYI, the North Pole is water, the South Pole is land. The North Pole is water and the South Pole is land. So I want you to actually collect 50 pieces of data. If you could fit your data up here in this little corner, then that will leave you more room. So I want you to tally the number of times that your globe lands on water versus land with your partner out of 50 times, and we'll end up getting a P hat for the proportion of times you got landing on water. What you came up with. So what we got is you are finding your proportion of water. So of course you want to put your number of water over 50 out of 50 trials to find your P hat for water. Okay, so now you could go back a couple of pages and you could then finish filling out your condition to see if you had at least 10 successes and at least 10 failures. Now, keep in mind, these successes will come out to be the number of water you had, and these failures here should come out to be the number of land that you had. Did anybody not have at least 10 successes and at least 10 failures? Good. All day long we've had at least 10 successes and at least 10 failures. So normal model applies. And so therefore we're allowed to do our normal model math. And so we're about to do that. Now, what I wanted to show you is that we are actually about to do our normal model math with something on the formula chart. And so I wanted to show you that here's the front of your formula chart, and on this front of the formula chart we have pretty much finished the front of the formula chart. So let's look at the back of the formula chart. So this back of the formula chart has got, guess what the title of this back side is? Inferential statistics, because for the whole rest of this year we're going to be dealing with inferencing about the entire population from one itty-bitty sample. So what I want to point out to you before we write it down is this formula right here. So what you could actually do is write this formula on your data page where your water is, right by where you wrote p hat. Your p hat. So I'm about to take this formula. It says to make a confidence interval, we're going to take our statistic plus or minus the critical value times the standard deviation of the statistic. So let me demonstrate that for you. Okay, so let me move this on away over here. So I'm going to write that out because we're going to break that formula down. So we're going to do this. So the confidence interval equals the statistic plus or minus the critical value times the standard deviation of the statistic. Okay? So we're going to break down this formula. So this, again, is available right there on your formula chart. And so what do you think? Do you think it is reasonable for you to take one sample and to say from that one sample that that is the population value for the proportion of water on that globe? Do you think you can do that, say that it is the population value? No. But do you think yours may be close to the population value? Yes. So what we're going to find, and so I want to give you a visual of what's about to happen. We're about to have your particular p hat, and then we're going to make a margin of error on the positive side and a margin of error on the negative side, and we expect that with certain confidence that somewhere in this thing we have captured the true proportion of water on that toy globe. Okay, so what we need to do is figure out what these numbers are that make this entire interval. What is the values down here at the bottom? What's the value up here at the top? How do we make this interval lower and upper bounds? And that's what this formula will do for us. In fact, the plus and the minus are the things that will make this upper whisker. When you add this amount, you make the upper whisker of the range. When you subtract this amount, you make that lower whisker. And in fact, this statistic is actually your p hat that you got. Okay, so your individual p hat that you got whenever you did your proportion of water on those globe tosses is that. Okay, these whiskers are actually called the margin of error. You might have heard that in political polls. You know, plus or minus 4% might be a common margin of error. So they'll get an estimate and then they have that margin of error. Okay, so mathematically then, let's take a look at these little pieces. Standard deviation of the statistic. How do we get standard deviation for proportion problems? Square root of p, 1 minus p over n. Very good. And the best it can be is if you use true p. But if you don't have that, you can just what? Use p hat. So you're going to have to put p hat in that and compute it. So I want you to take a moment and compute this on your particular p hat. So do that now. By the way, sometimes this standard deviation is called standard error because it is made from p hats, and that makes people nervous because it's made from a p hat and not a true p. So sometimes it'll be referred to as not standard deviation, but standard error. Okay? So at this point, you should have your particular standard deviation for your p hat. Okay. Now let's talk about this thing right here. This next thing is a critical value. It will be represented by Z star. It is similar, but not the same as a z-score. So probably tomorrow or the next day, I'll really clarify what the difference is between those. And it's not, it's just a matter of, are you given it or are you finding it? So this z-star, this critical value, is always found using the confidence level that you are asked to have. For example, today I'm going to have you be 95% confident that the true proportion of water on your globe is found in your interval. So if I ask you to be 95% confident, listen here, if I ask you to be 95% confident, z-star is not 0.95. That percent is not the z. It's still not the z. That percent confidence is still not the z, but we will use it to get the z. And there's a short little mini lesson on the next page of how we get a critical value. So if you'll turn over to page 4, we'll get that critical value real quick. So there's 3. A common amount of confidence is 90%. They may say be 90% confident, 95% confident, 99% confident. Those are common confidence levels. But here is how you do it. First step, put the confidence level in the middle of a normal model. Put the confidence level as the middle area. So in this case, we're going to do an example for a 90% confidence interval. So we're going to put 90% of the data. We want 90% of the data in the middle. And if we have 90% in the middle, then the second step is determine the amount, the area in a tail. Determine the area in each tail. So I want the odds to tell the evens right now. How much area is in each one of those tails if 90% is in the middle? Okay, go. Okay, so what'd you come up with? Odds told the evens, so the evens tell me how much area is in each one of those tails. Clayton, what do you guys? 10%. 10% total?
5%.
So therefore, each tail will contain 5%. Very good. Okay. So now, a critical value. The critical value, the Z star is these boundary points. That is what the Z star is, where the Z star is located. Okay? So you have a lower Z star and an upper Z star, and those are the bounds, that the cutoff locations that contain 90% in the middle. So the third step then to get that value is to do inverse norm of one tail. So for example, this problem up here would be inverse norm of 0.05, and that is negative 1.6449. Okay, so the odds told the even last time, so evens tell the odds. Why? Inverse norm of 0.05 is a negative z-score. Go. Why inverse norm of 0.05 is negative z-score? Okay, so what'd you come up with? Odds over here. What'd you guys come up with? Why is it a negative z-score?
Because inverse norm is the area below.
Okay, I get that. That's a common thing that people say. Inverse norm is the area below, and that is not why. It is a negative z-score. It is not a negative z-score because inverse norm is the area below. Why is it a negative z-score? Because this is located, where is that located? To the left of the mean. Now it is related to there only being 5% below it. 5% below it puts it in the left side of the mean. That's why it's a negative z-score. Now, because of symmetry, what is this other critical value up here on the positive side? Same thing. It is positive 1.6449. So in summary, for a 90% confidence level, the critical values, and there are two of them, are positive and negative 1.64. Okay, so I want you to take a moment and follow those steps and find the critical value based off of 95% confidence, because that's what I'm going to have you make in a minute. Find the critical value for 95% confidence level. Okay, so if you have 95% in the middle, that's 2.5% on both tails. Inverse norm of 0.025 is negative 1.96, but we know it is the both. There are two critical values, the positive 1.96 and the negative 1.96. Okay, so that was the short little mini lesson. Now, let's take that back over to compute your water critical or confidence interval. So I would like for you now to compute your confidence interval using your p-hat plus or minus the critical value you just computed and using the standard deviation. So in other words, you'll take your p-hat plus this product in the back and your p-hat minus this product in the back. That's how you get a lower number and a higher number. And the format of your final answer will be an ordered pair with the lower bound on the bottom and the upper bound on the top. So I want you to compute that right now. For example, you might get something like 0.42 and 0.64. So that's an example of the format you might get. Okay, so let me give you a moment to compute that in words. So what we would say is, I am 95% confident that the true proportion of water on the toy globe is between, and then your lower number and your higher number. So 42% and 64%, or whatever values you've got. And so that's the process that I want you to do 5 times on the homework. And the homework starts on page 6. And so here we go. We got this problem here. And let's kind of look at it real quick. Number 1, and so again, this is page 6, and we're going to do, you'll be doing pages 6 and 7 as your assignment. So number 1 says, for a sample of 100 European coins, the probability of landing on heads is 0.73. All right, so what variable is 0.73 representing? It's obviously a proportion. Is it p or p-hat? It's p-hat because that's the thing that they got off of 100, a sample of 100. So they did that European coin, they flipped it 100 times, and they had 73% of those landing on heads. So then, of course, from that, you could figure out your standard deviation of p hat and so on. But you'll also then have to figure out your critical values, which will be plus or minus. And it's a 90% confidence interval. So you'll want to use this technique of knowing if 90%'s in the middle, then 5%'s in a tail, and so on. So this says, first identify the critical value for 90%. Do you recall what that was for 90%? Good. So that's your plus or minus 1.64. We actually did the work on that on the previous page. And then here for your work, of course, you'll be using your formula. Okay. And the interpretation in context, these are the words that you will be doing. Okay, I am 90% confident that the true proportion of time, in fact, look at this information right here. The true proportion of times this particular European coin lands on heads is between blank and blank % of the time. So make sure you are clear on what you are actually estimating so that you can use this type of language in your interpretation. All right, that's it. So you guys have got time. I'm going to come around and get all of your intervals so that I can include it in my class data. And there you go. So I'll come around and get that from you.